Welcome back to Honors Calculus. In this video, we're going to be taking a break from what we've been talking about to go over summation notation. Depending on your path that brought you to this course, you may or may not have seen summation notation in the past. Summation notation is a tool we can use for adding together a number of things that are related in a pattern but not the same. When you've dealt with repeated addition in previous courses, you've looked only at the simplest case of repeatedly adding the same thing over and over again. Adding the same thing over and over again is the definition of multiplication. We want to, in this lesson, add different things together, but those things have some sort of pattern or predictable behavior. We call that pattern a sequence of numbers. So let me get my head out of the way and let's start with that definition. Right. A sequence is going to be denoted A with a subscript of K. Sometimes you'll see a subscript of I, sometimes you'll see a subscript of N. I like subscript K. And we're going to put that inside of curly braces, which are not quite going to function as set braces, but similar enough for most purposes. And a sequence is a function. It is a function instead of taking a real variable and mapping it to a real numbered output. We're going to take a natural number input. So that's why we use the subscript instead of A of K. Right? Subscript to indicate that K has to be in the natural numbers, 1, 2, 3, 4, 5, and so on. Right? No fractions, no negative numbers, no irrational numbers. Even 0 is usually out. I say usually, sometimes it makes sense to include 0 in the natural numbers, sometimes it does not, depending on your particular context and your particular needs. We can define sequences in any number of ways. For our purposes, for right now, we're going to stick with sequences that are defined pretty nicely in the polynomials. So for example, if I have AK equals K squared minus 1, then plugging in K equals 1, 1 squared minus 1 is 0. Plugging in K equals 2, 2 squared is 4, 4 minus 1 is 3. Then we'll have 9 minus 1 is 8, 16 minus 1 is 15, 25 minus 1 is 24, and so on and so on. All right, all the numbers K squared minus 1. So that's what we mean when we say a sequence. All right, a summation is built on a sequence. For some sequence A, mapping from the natural numbers to the real numbers, we're going to define sigma AK. And we're going to put down here K equals 1, and we're going to put up here sum n. And we needed to have that n itself be a natural number. We'll read this. First of all, the symbol there is the Greek letter capital sigma. It kind of looks like an E, or maybe an M turned on its side. If you want to put serifs in it, you can. They show up in all these places, and it's usually written in a serifed font. Um, and we'll read that as the sum of AK for k equals 1 to n, or sometimes the sum going from 1 to n of AK, or any variant on that basic idea. Mathematically, follows exactly what that statement says. We take k equals 1, we take k equals 2, and we keep adding these things all together until we get to an. For those of you who are continuing onward to study further mathematics, a little bit later in the calculus sequence, we will revisit this idea of summation notation, realize that a summation itself is a sequence for different values of capital N, and we can then use it as such. I'll go through a quick example here. Make sure that the basic idea makes sense. For example, if I want to take the sum, k goes from 1 to 5, of k squared minus 1. Well, we already wrote out these first couple of terms. Plug in k equals 1. 1 squared minus 1 is 0. Plug in k equals 2. 2 squared minus 1 is 3. Plug in k equals 3. 3 squared minus 1 is 8. Then we get 15, and then we get 24. And if we add these things together, 0 plus 3 is 3, 3 plus 8 is 11, 11 plus 15 is 26, 26 plus 24 is 50. And so that's what summation notation is telling us to do. It's telling us how to add some things together. Well, that's well and good, but it would be nice if we didn't have to literally add all of the pieces together in order to actually evaluate the summation. And in fact, we don't need to do that. We have a theorem here called the common summations. Proving this theorem is a little bit beyond the scope of this course. I know that's a little bit surprising to say given some of the things that we have proven. But for those of you who are moving onward to eventually take a course in discrete mathematics, one of the things that you learn in that class is how to prove these rules on common summations. Right. There are 4 common summations that I want to look at. The sum k goes from 1 to n of 1 is equal to n. The sum k goes from 1 to n of k is n times n plus 1 all over 2. the sum k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6, and the sum k goes from 1 to n of k cubed is n squared times n plus 1 squared all over 4. And as I said, I don't have the tools that we need to prove these summations, but I suppose we could at least verify one of them. For example, the sum k goes from 1 to 5 of k is 1 plus 2 plus 3 plus 4 plus 5. Right? 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. Or, using the summation rule, this is going to be 5 times 5 plus 1 all over 2. 5 plus 1 is 6, 5 times 6 is 30, 30 divided by 2 is 15. So it's not a proof, but it is a way of verifying that you get the same thing either way. Again, those of you who are moving onward to eventually take a course in discrete mathematics, this is something that you will revisit in that class, and you will learn the technique needed to prove it. But it would take me a full class period just to do that, and that's not what I'm interested in here. What I'm interested in here is actually using this. Although we do have a tool that I do want to prove here. I claim that summations are linear. Remember what we've talked about before with linear operators. If I have a summation, k goes from 1 to n to be generic about it, of a linear combination of sequences. Some constant, let's go with p, times some sequence, ak, plus some other constant, let's go with q, times some other sequence, let's go with bk, I claim is going to be equal to p times the sum, k goes from 1 to n, of ak plus q times the sum, k goes from 1 to n, of bk. And this particular summation is pretty easy to prove, or this particular rule of summation is fairly easy to prove, because we can just use the definition of the summation. I'm going to be a little bit lazy, and I'm going to suppress the k goes from 1 to n on all of my summations. For our purposes in this lesson, it's always going to be the same. Moving onward beyond Calc 1, or even later on in this lesson, we're going to look at breaking up summations and talk about two different things. But for right now, everything is the same, and I'm going to be lazy. But the definition of a summation says that we're going to add P A1 plus Q B1 plus P A2 plus Q B2, and we're going to keep going until we get to PAN plus QBN. But this is a bunch of stuff added together. And we have the commutative and associative properties of addition, which tell us that we can rearrange this. And we can separately think about, oops, wrong pen. We can separately think about PA1 plus PA2 plus dot 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 plus PAN, and we can separately think about QB1 plus QB2 plus dot 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 plus QBN. There's nothing stopping that. Then from the first group, we can factor out a P. And from the second group, we can factor out the common factor of Q. And then we realize that the stuff in parentheses is just the sum on AK and the sum on BK, which is exactly what we said we were going to conclude. So this idea of linearity for summations is really just the commutative, associative, and distributive properties of addition. We can use commutative and associative to rearrange the summation in an order that makes sense. We can use the distributive property to factor out the common factor of P and of Q. And that's all we're doing when we rewrite a summation. And so if we have something like the sum k goes from 1 to 25 of k squared minus 1, we could go and write out all 25 terms, 0 plus 3 plus 8 plus 15 plus 24 plus 35, 48, 63, 80, 99, 120, 143, and keep going. It would work. It would take some writing, but it would work. Instead, I want to use the linearity. I want to break this summation up and separately think about the sum. K goes from 1 to 25 of k squared, and separately think about the sum. K goes from 1 to 25 of 1. Using our rules of summations, the sum on k squared is n, which is 25, times n plus 1. 25 plus 1 is 26, times 2n plus 1. 2 times 25 is 50. 50 plus 1 is 51. All over 6. The sum on 1 is n, which is 25 in this case. All right, grab out my calculator. 25 times 26 times 51. My calculator tells me is 33,150. Divide that by 6, my calculator tells me is 5,525. Then subtract 25 to get 5,500. Let's look at another one, a little bit more complicated. The sum, k goes from 1 to 300 of 2k plus 5, the whole thing squared. Our rules for summations allow us to break up the sum over a linear combination. But in this function, in this sequence, the square is happening at the end. So this is not a linear combination, but a nonlinear combination. But that won't stop us. We know how to square a binomial. 2k plus 5, the whole thing squared, means 2k plus 5 times 2k plus 5. Well, 2k times 2k is 4k squared. 2k times 5 is 10k. We'll have two of those. All told, that's 20k. And then 5 squared is 25. Now we can use linearity to get 4 times the sum on k squared, 20 times the sum on k, and 25 times the sum on 1. And then using our summation rules, k squared is going to be n, 300, times n plus 1, 301, times 2n plus 1, 601, all over 6. The sum on k is going to be n, 300, times n plus 1, 301, all over 2. And the sum on 1 is n, which is 300 in this case. My calculator is very happy to tell me that 300 times 301 times 601 divided by 6 is something in the ballpark of 9 million, and then we'll multiply by the 4 in front to get 36,180,200. Then we'll take 300 times 301 divided by 2, which is 45,150, but there's a 20 in front, so we'll multiply that as well and get 903,000. And then we've got 25 times 300, which is 7,500. One last step, adding these things together, 36,180,200 plus 903,000 plus 7,500, my calculator tells me is 37,090,700. It looks really messy, but it's just a game of doing some computations. All right. I would like you to try something very similar. The sum k goes from 1 to 120 of 3k minus 5, the whole thing squared. Right? Look at that last example. Try to go through this one using a similar process. You will want to use a calculator for this. Run through that calculation and let me know what you come up with. Right? See what you can do with that problem, and I'll see you in the next video.